We talk about speed all the time, right? Like how fast your car goes. But chemical reactions, they have a speed too. Some are over in a flash, while others, they can take years. So what's the gas pedal for the world of chemistry? Let's dive in and find out.
I mean, have you ever really thought about this? Why does a carton of milk go bad in like a day on your kitchen counter, but it's totally fine for a week in the fridge? It seems simple, but the answer to that question is actually connected to the same reason a campfire needs a match to even get started. It really all comes down to the speed of chemistry and the energy it takes to kick things off.
Okay, check this out. This is the whole idea in action right here. You see, when we add some bleach to food dye in cool water, yeah, the reaction is pretty slow. But watch what happens in the hot water. Bam! The color just vanishes almost instantly. That is the power of temperature, and we're about to unpack exactly why it's so effective.
So there's actually a whole field of science dedicated to this stuff. It's called chemical kinetics. And really, it just boils down to asking two main questions about any reaction you can think of. First, how fast does it go? And second, how does it actually happen? What's the play-by-play, the step-by-step mechanism?
All right, so here's the plan. First, we'll talk about why reactions even have a speed to begin with. Then we'll get into the big energy hill they all have to climb. After that, we'll see how turning up the heat helps, look at the cool equation that maps it all out, and finish up with a really clever shortcut called a catalyst.
Okay, let's jump right into part one, why reactions even have a speed. To really get this, you have to think about a chemical reaction like a journey. It's got a clear starting point and a definite finish line.
So every journey needs a starting line, right? In the world of chemistry, our starting ingredients are called reactants. This is the stuff you have before any of the action begins.
And if you have a starting line, you've got to have a finish line. In this case, that's our products. These are the totally new things that are formed once the reaction is all done. So when we talk about the speed of a reaction, we're really just asking, how fast can we get from our reactants to our products?
But here's the thing. Getting from point A to point B is almost never a simple, flat road. And that brings us to section 2, because there is often this huge obstacle standing right in the middle of the path.
So this is really the key. That path from our reactants to our products, it's not flat, not at all. Molecules can't just stroll over. They have to climb a big energy hill first. I like to think of it like you have to push a huge boulder up a short hill before it can go rolling down the much bigger hill on the other side. And this energy hill, it has a proper name. We call it the activation energy. It's like the entry fee for the reaction. It is the absolute minimum amount of energy the reactants need to get the whole thing started. If they don't have it, nothing happens, period.
Yeah, exactly. As one source puts it so well, the reactants have to surmount a reaction barrier. And you can probably guess, the height of that barrier is the single biggest factor that determines whether a reaction is super fast or incredibly slow.
Okay, so if these little molecules need a bunch of energy to get over this hill, how in the world do we give it to them? Well, that's what section 3 is all about, turning up the heat. All right, this graph right here, this basically explains everything. At any given temperature, molecules are all moving at different speeds, right? They have a whole range of energies. Now look at that blue curve. That's a lower temperature. You can see that only a teeny tiny fraction of those molecules have enough juice to get over that energy barrier we just talked about. But when you add heat, look what happens to the curve. It shifts over to the right. And that shaded area, the number of molecules that now have enough energy to make the climb, it gets way, way bigger. So here's the big takeaway. Turning up the heat doesn't magically give every single molecule enough energy. But what it does do is dramatically increase the percentage of molecules that can successfully make that climb. And more molecules making it over the hill means, you guessed it, a much faster reaction.
Now scientists, they weren't just happy knowing that hotter is faster. They wanted to put a number on it. They needed an actual formula to map out this whole mountain climb. And that brings us to the famous Arrhenius equation.
And there it is. Now, I know, it might look a little scary at first, but trust me, it's not so bad. Think of this equation as the mathematical recipe for reaction speed. It's the code that perfectly links together everything we've talked about, that energy hill, the temperature, and the speed of the reaction. Let's just quickly break it down. That K on the left, that's the reaction speed we're trying to figure out. The EA, that's our activation energy, the height of that hill. T is, of course, the temperature. That's our gas pedal. And that A at the front is basically a factor that takes into account how often the molecules bump into each other in just the right orientation to actually work.
But look, you don't need to be a math whiz here. The most important thing to pull from this equation is an awesome rule of thumb. For a whole lot of common reactions, just raising the temperature by 10 degrees Celsius, that's about 18 degrees Fahrenheit, can literally double the speed of the reaction. That's why leaving the milk out is such a big deal. A few hours at a slightly warmer temperature makes a massive difference.
Okay, but what if you're in a situation where you need a reaction to go faster, but you can't just, set it on fire? Maybe heating it up would destroy the product. Well, that's where we find a clever little shortcut: catalysts. And this is the brilliant part. This is the real aha moment. Instead of trying to give the molecules more energy to get over that same tall hill, a catalyst just creates a whole new path, a shortcut with a much, much lower activation energy. It's literally like discovering a tunnel that goes straight through the mountain instead of having to climb all the way over the top.
And you know what's really cool? The catalyst itself doesn't get used up in the reaction. It's like an expert mountain guide that just shows the reactants a faster, easier trail to get to their destination. Once they're through, the guide is ready for the next group. It just works by lowering that energy barrier.
And believe me, this isn't some abstract chemistry concept. It's happening inside your car every single day. The catalytic converter, it uses metals, like platinum, to create a surface where harmful pollutant molecules can find that easy shortcut. They react super fast, turning into harmless gases like nitrogen and oxygen before they ever even leave your car's exhaust pipe.
So it kind of leaves you with this thought, right? We've seen that temperature is the gas pedal, and a catalyst is the ultimate shortcut. And if a tiny change in temperature can literally double the speed of chemistry, it makes you wonder, what other invisible energy hills are being climbed and lowered all around us, all the time? From something as simple as an egg frying in a pan to the trillions upon trillions of reactions keeping you alive right now, chemistry is always finding a way to get over that mountain.